So today we are going to talk about a special kind of cryptographic primitives known as symmetric key. So we have already talked about a bit about cryptography. So there the basic idea is that it has two components. So one is for encryption, another one is for decryption. So in the encryption algorithm, the plain text is been given. So I represent it by M, and then a key is also used. Then it will generate ciphertext. I denote it by C. Then the ciphertext moves through insecure channel where some attacker may see the ciphertext, and then it reaches to the person to whom the message is being sent. So in the decryption algorithm, the ciphertext is being inserted. Also, there will be some key, and it will certainly generate, if everything goes well, then it will certainly generate the original plain text, the same as the original plain text here. Okay. So that's the basic idea of cryptography, where the ciphertext usually travels through some insecure channel, and we assume that everything except this key is not known to the attacker. Okay. That means the plain text is certainly not known to the attacker, but this algorithm for encryption as well as decryption is known to the attacker. Since the ciphertext is traveling through insecure channel, the ciphertext is also known to the attacker. So the attacker knows the encryption algorithm, the decryption algorithm, and all the matters related to this encryption and decryption algorithm. Okay, and he also knows the C. So the attacker's aim is to find sometimes this aim, or most of the time to find the keys, because if he by some means if he comes to know the key, then it may be helpful for him or her to decrypt the other messages as well. That's why sometimes the attackers, they try to guess what could be the keys. Okay, so that's the basic idea. This is the basic general setup for any cryptographic scheme. But here there is two types of cryptographic scheme, broadly speaking, depending on the keys. If this encryption as well as the decryption keys are happen to be the same, then we call it symmetric key. Symmetric key crypto system, or this is also known as private key. And if these keys are happen to be the not same, then we call it asymmetric key or public key crypto system, PKC, public key crypto system. Okay, for example, we have already seen this RSA crypto system or Elgamal crypto system. Okay, and also for symmetric key, today's class we are going to see few of them. So that's the target for today's class. Okay, so that means for symmetric key we will have these two keys that happen to be the same. That means we will use in both cases K. Okay, now in case of symmetric key we will again have two branches. So symmetric key again has mostly two branches. One is stream cipher, another one is block cipher. In today's class, we shall try to highlight this stream cipher. Okay, so the name suggests that some stream is there. So we will show that in stream cipher there will be a stream of keys. The keys will be coming as a form of streams, like stream of water, like that. So in stream cipher we will also see the key will be coming as a kind of stream of keys. That's why the name stream cipher came into picture. Okay, So let's have a look at in a simple way. So this is my encryption algorithm. So it takes as an input some input. Suppose my input is, say, like this. Say this is 8-bit long input. So it's a binary. For this binary, suppose I have a key. So the question is, how do I generate a key? For example, suppose I have a key. Say my key is, say, 0011010110 1 2 3 4 1 2 3 4 1 2 3 4. So this is extra, so I can remove it. Okay, so 8-bit. So this is also 8-bit, this is also 8-bit. Now we call this as stream of keys. Okay, so I can write it like this: K1, K2, K3, K8. Similarly, for message M, we can write it like M1, M2, M3 dot dot M8. Okay, so the question is, how do I combine these two? In case of a simple, in case of a stream cipher, most of the cases, what is happening here is a very simple operation known as Xor operation. So Xor operation is very simple one. How we can define Xor operation? So if I consider the bitwise Xor operation, then both the operands are in binary. So let's have a look at the truth table. So if you do 0 0, it will give you 0. If it is 0 1, it gives you 1. If it is 1 0, it gives you 1. But again, if both of them are 1, then it gives you 0. So that's the truth table for XOR operation for engineers, especially for electrical or electronics or computer scientists. For them, this XOR operation is very common. But for mathematician, don't worry, the same operation can also be thought as addition modulo 2. So just consider Z2 plus group, and you consider this as an element of Z2, either 0 or 1. So what we know, in case of Z2, if you add 0 plus 0, it becomes 0. If you add 0 plus 1, it becomes 1. If you add 1 plus 0, it becomes 1. But if you add 1 plus 1, then that becomes 2. But in Z2, the value of 2 becomes 0. So it's the same thing. So XOR operation is same as the Z2 addition. Okay, that means the truth table for this is very simple and very familiar to both engineers as well as to mathematicians. So here also it will be done in that way. That means here my plain text is 100111010 and my key is 00110101 and simply do the bitwise XOR operation. So usually it is written in this form, plus and then circle. So as I just now, it's a bitwise XOR operation. So it will be 11110 and then 0 and this is 1. Okay. So as a cipher text, what I am going to get is this is mi plus ki, and that will be represented as 1010111. Okay, so this is my cipher text. So this is my CIs. So C equal to C1, C2 up to C8. Now this will travel through some insecure channel, and when it will be received by the recipient will receive as ciphertext C. Note that we are talking about symmetric key. As a result, the keys will be the same in both sides. So here we are also going to use the same key. That means we are going to use 00110101 as our key. So this is my K1, K2, K8. Now this is my ciphertext. Now what is my ciphertext? So this is my ciphertext. So this is my 10101111. And what is my key then? Key is 0011101. Then if I do a bitwise XOR of it, what should I get? So 01011001. And if you look at this, this is same as the plain text. Okay. So the recipient will receive M equal to M1, M2, M8 by doing the operation Ci XOR Ki. Okay. So the operation is very simple, and you will be surprised to know that if you do like XOR operation in hardware, the hardware implementation is also very fast. As a result, this is very useful in practical purposes. That means when we require lots of bits to be sent, for example, when we talk through internet or mobile, then our voice signal is usually converted into, suppose I make a call from here. So this is suppose my mobile. When I make a call, it actually first tries to go to some antenna. Okay. So you might have seen some mobile towers are there. So it reaches to the mobile tower, and then through mobile tower, some base stations are there. Through base station, to whom you are calling, suppose you are calling to somebody who is suppose here with his or her mobile. Okay. Now this location may be within the range of some tower, mobile tower. Okay. So when you call to this mobile first contacts to its nearest mobile tower, then this mobile tower goes to some base station, and from that base station it tries to find to whom you are going to call, their base stations, their tower or their base station first, and then from their base station it's connected to the tower which is nearest to the person to whom you are going to call. And then from there it goes to their signal goes to this, and then it is connected, and if he picks up the phone, then both of them, then they can communicate with each other. So the voice is first. So when you talk, suppose you talk in English or in any language, then the voice is getting converted into some binaries, and then from binaries to signals, and then from here some optical cables, it goes through optical cables, again from here some signals, and then again from there to binary, and then from binary to again voice. So a lot of transformations are being done here. And believe me, in this mobile also they use some of the encryption schemes, and you can understand that you need to make it very fast, otherwise there will be a delay or maybe a lot of noise may come. That's why you require a very first encryption and decryption process, and there the stream ciphers are considered to be one of the most important or most practical or most applicable things in cryptography. That's why for mobile encryption or for online streaming, wherever you require fast encryption, stream cipher is considered to be one of the very good choices, unlike the public key crypto system. For example, RSA. So there you have to do a lot of computation for sending a bunch of or a chunk of message. So that requires lot of computations powers, and it's compared to this, the RSA encryption is quite slow. So for this kind of purposes, the mobile encryption or something, the stream ciphers are heavily used. There are plenty of other places where stream ciphers are heavily used. I mean, for symmetric crypto system, mostly, for example, like protocols like TLS or SSL. So everywhere you will find that. We'll come to it later on when we are going to teach you about the block cipher as well. Then you will find that in many protocols, the stream ciphers as well as block ciphers, so mostly the symmetric keys are heavily used. Okay. So the question is, if this is the case, then for both sender as well as the receiver, they must use the same set of keys. If they are not the same, you will not get the same message, right? So that is very important. That's why they are symmetric. And when you think about this, few encryption schemes are very common, and they are well studied in the domain of cryptography. I will first give you one of the very important example of that. Okay. So first think about, in case of a symmetric key, both the keys, this and this, they must be sent. So they must know the same key, and that keys has to be synchronized. For example, you cannot start with K4 because then that will decrypt a different message. If you start with K4 and M1, then Xor of that will give you a different message. So synchronization is also important. At the same time, at both the ends, the same keys must be available to get the actual effect of symmetric key. Okay. So to understand that, first let us try to have a look at a very historical one, and that is known as one-time pad. So I have taken it from directly from Wikipedia. So you can also Google it, and you can see in Wikipedia. It's quite well known. It's also available in any of the books. Okay, the idea is here very simple, and it came historically. If you look at this, it came around for the first time around 1882 by Frank Miller, but then as name as one-time pad. So here it's mentioned that don't OTP. So the OTP. So one-time pad, it's also abbreviated as OTP. So it says that don't mess with one-time password. So it's different. So the name, though it both of them are OTP, but this is one-time pad. But now what we use as OTP is one-time password. So both the things are not the same. Okay. So it was first invented in 1882, according to Wikipedia, by Frank Miller, but it was then as a one-time pad. It became famous when it was reinvented in 1917 by Barnum. So this is sometimes it's also known as Barnum cipher. So Gilbert Barnum in 1917, and it was patented in 1919, US patented. Okay. So what it uses actually? So what is the idea? Exactly the same what I have just now explained. Okay. So suppose, so if you, I will show you later on, but most importantly, it can be proved theoretically that this one-time pad cannot be cracked. That means, what does it mean actually? I will come to it later on, but it's very secure provided you follow the following facts. It says that the key must have a uniform distribution that is independent of the plain text. What does it mean? That means you are going to use the keys. So you are going to use the keys here. So that keys should be uniformly distributed. Okay. So that key should be uniformly distributed, and it should be independent of the plain text. That means there should not be any relation between the plain text and the keys. So the first question that comes to our mind is, how can I get a simple way of getting such kind of uniformly distributed keys? Okay. Suppose my key is, so that actually gives you the idea of randomness, right? So what I need some random looking key stream bits. For example, suppose I write 10101010. So it's 8-bit long. And do you think that it is quite normal as a random bit? So I think all of you must have some idea about randomness, right? That means, for example, what is the simplest example of getting some random number or getting some random event? It's very simple. If you have a, say, any coin of whatever, it may be rupees, it may be a dollar, it may be a yen, it may be a pound, whatever it may be, start with that coin and you make a coin toss. Okay. Suppose I get head. So I get head, I just put 1. So if I just made a kind of notation that if I get head, I will put 1, and if I get tail, I will put 0. So first one, I get a head. So I put 1. Let's again do it once again. I get tail. So it's 0. Again, I do it. I get tail. I put 0. Again, I do it. I get head. I put 1. Again, I do it. I get a tail. I put 0. Again, I do it. I get tail again, I put 0. Again, I do it, I get a head, I put 1. How many? 1, 2, 3, 4. One more, let's see. I get another head. Okay. So you can see that it's a like 1 0 0 1 0 0 1 1. So it's an output of an event which is basically coin tossing event. So if this coin is an unbiased one, that means if the probability of getting head, so if x is my random variable and if the probability of getting head means 1, if this is half, same as probability of getting 0. If that may be the case, then we call this as an unbiased coin. Okay. Now you can see that here suddenly we get 4 heads and 4 tails here in my 8 consecutive coin tossing event. Okay. So if I write in this way, if my case like this, and if I ask you, is it really random? So what is your idea? Do you think that this is a random sequence? What is your idea? Anybody?
No, sir. It is a
So it
pattern.
has some
No, sir.
pattern, right? So it has some pattern. So you may discuss this as a random sequence. Okay. Okay. If somebody says like this, and if I put like this, and if I ask you, do you think that this is a random sequence? Again, you will say that, okay, that there is a, pattern of it. So it is also not. If like this 1 1 0 0 1 1 0 0, then that will also be not a pattern. Okay. This is a pattern, so you can also discard it as a kind of random, so as a random sequence. So now you have something at your mind that, okay, if I make a, say, 100 times coin tossing event, so I'm going to toss it for 100 times, and with a coin, just like whatever may be the currency, you can always have a coin. And suppose you make a coin toss event, and so you will have some like this, like this kind of sequence will come, say like this, and then you need to judge whether that is a random or not. Okay. So intuitively you can understand that if the probability of getting head and tail is exactly half, then it is expected almost all the time that if you do 100 times of coin tossing, then the number of heads and number of tails must be around, not maybe exactly the same, but must be around 50-50, right? 50 plus 50. It may happen that 46 plus 54, it may happen that 41 plus 59. That depends on your throwing the coin, and in that case it may not be a properly unbiased coin, but mostly roughly if you start with any of the coins and if you do 100 times coin tossing, then you can understand that the number of zeros and ones, that means number of head and tails, will be almost same, right? Now I asked my student to have a game, like the game will be like this. So first the students will generate a random string from their own, that means, so this will be the random looking string, and that will be generated randomly without doing any kind of experiment. That means first a student will think, just closing their eyes and just think either 0 or 1. So suppose I think like 0 0, sorry, 1 1 0 0 1 1 0 0 0 0 1 1 1 0 0 1 1 0 0 1 1, just keeping in the mind that you are actually trying to simulate the 100 digit long or 100 bit long random sequence. Okay, just from arbitrarily whatever you think, either 0 or 1, you write it down, but keeping in mind that you want to generate a random looking bits, 100 bit long string. Okay, so you can understand that it should not have any kind of pattern, and also you understood a bit that the number of zeros and ones will be around 50-50. Around 50-50. That you need to keep in your mind, but because you know a little bit of randomness, or if you know a little bit of idea about the probability theory. Okay. So you get ultimately, suppose this is a 100 bit long, 100-bit long string generated by you. Okay. Now, so this is say my 1, and now you need to do some experiment. Take any coin of your as you wish, and make a coin toss 100 times. And suppose you have written head with 1 and tail with 0. So if you do it 100 times, then suddenly you will get some sequence of zeros and ones like this. So this is also 100 times, 100 bit long, but generated through coin tossing. Generated through coin tossing. Okay. So I asked my students to provide me with these two strings. So it may be 1, it may be 2, you can permute it, whatever it may be. But you do not tell me which sequence is generated from coin tossing and which sequence is generated by you. Okay. It will be my observation to tell you that, okay, suppose I will give me 2 of them. Just by looking at some information or some pattern inside this, I will able to guess, or I will able to almost with certainty, I will able to tell you that which sequence is the sequence which are made by using this 100 times coin tossing, or which sequence that you made on your own without doing any experiment. Okay. I requested my students to do so. I am sure that my students have already made this. So let's have a look at this. So anybody is having with this sequence, please share your screen. I'm stopping my screen. So Aniket is now presenting. Okay, let's see. Okay, so your second one is the one which you obtained through coin tossing, and the first one you did it by on your own. You did it on your own. Is it correct?
Yes, sir.
Okay, thank you. So anybody else?
Sir, I am present.
Yes, sir. Can I share?
Please. Okay, it's very small. Let's see. It's really difficult for me to guess which one is coming from what, because both the things are generated quite nicely. I mean, it's really difficult. I will tell you by using property, I am going to tell you that whether this is, but what I think that this is, the second was is generated from, the second one is generated from the coin tossing, and the first one is generated on your own. Is it okay?
No, sir. The first one is the coin toss.
Okay. Yeah, as I mentioned, it's really difficult to guess which one is from where. I will tell you why is it is difficult, but it was nicely made. Okay. Any other, anybody else?
Okay, sir, I am presenting.
Yeah. Okay. This one, right one is generated by coin tossing, and the left one is generated by your own.
Yes, sir, right.
Okay, so why I am telling like this? Yeah, so the point is, it's a very simple mathematics. It's nothing else. It's simple mathematics that you need to calculate a simple probability. I'm going to give you just the idea, but it is a kind of homework that you need to do. Okay. So it's basically the calculation of an expected value. Okay, so it's a simple calculation of probability. The idea is like this. The idea is, so the probability of, I'm trying to calculate that the probability of getting in consecutive heads. Okay, so I'm trying to find what is the probability of getting in consecutive heads. In other way, we can find a kind of expectation that how many trials are required to generate at least say 5 consecutive heads, or at least 4 consecutive heads. How many trials are required to get? That means you are going to find some expected value. Okay, and it can be shown that you can very easily find. So I'm just giving you this as an homework to find this expectation value. And it could be found that if you do around, if your coin is unbiased one, if your coin is an unbiased one, then the expected value is around 64. That means if you do 64 trials of doing this head and tail experiment, then you will have, it is expected that you will have one run of consecutive heads like this. Okay, so you are doing it like 100 times. So it is expected, very much expected, that there will be a trail of consecutive 5 or even sometimes 6. So if you do like 6 consecutive heads within 100, then you will have run of 6 consecutive heads. Okay, so that's why that is the point that I am going to show you, that when I get the strings, so when you are going to generate a random number with the information that you have, is it should not have any pattern. First one, no pattern, and then you want to have around 50% of head and 50% tail, right? So these two things are there with all of us, right? When we are going to generate this, then what usually we'll do, when we put some like 1 1 1, then when you put another, when you are thinking of putting another one, your conscious bid will stop you to do so, because it will ask you, okay, am not I putting, isn't I putting more one here consecutive? Then that may, because at the end I need to put 100 ones, and that too around 50% of tails and 50% of heads. So when you put like another one, then already you have given 4 ones. So you may think that, okay, why not some 0? So when you do so, then the probability of getting like 4 consecutive ones or 5 consecutive ones is very less. Whereas when you do the coin tossing, you will find that you will have a trail of, you may find a trail of maybe 6 or maybe 7 or maybe 8 consecutive ones. That is quite unusual when you are going to do on your own without doing any calculation. That's why when I did it for the second one, when I think who asked, who gave us the second one, which I did wrong?
Yes, me.
Okay, so I think Paulomi gave me. And if you just once again, if you just share with your, I'm stopping my presentation. If you could share your once again, then you see that in both cases you have a lot of 0 1 pattern. See, here also you have 0 1 pattern, too many consecutive zeros, too many consecutive zeros. That's why when she showed us, at that time I told that both of them are nicely generated. That's why it's very difficult for us to distinguish whether this is a random or not. But if you look at the first one, who gave the first one? And who gave the first one? Oniket, I guess.
Yes, sir.
Oniket, could you please share again?
Okay.
Yes, thank you. If you see that, here you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and there is none of them here, so there may be more. So 1, 2, 3, 4, 5. So this consecutive heads and tails are more here than this. And see here you have only at maybe a 4 consecutive one. 1, 2, 3, 4, 4 consecutive one. So you can then very easily tell that okay, this one is generated through coin tossing and this one with his own. Okay, so that was the simple mathematics. You can do it, and if you do it for 1,000, if you do it a coin toss for 1,000, then the probability of losing it will be again less, because then you'll find that there may be a consecutive 15 or maybe consecutive 20 patterns will be there in coin tossing case, and it will be really very difficult unless you know this problem, then to have maybe 15 consecutive ones or 15 consecutive zeros all put together. Then if you do it for 1,000 penny coin tossing, then almost with probability 1 we will able to win the game, but it's really pathetic to do 100 times or 1,000 times coin tossing. That's why to do it with 100, I think it's fine. Okay, so yeah, please, thank you. Aniket, please, could you please off your screen? Okay, so now some idea of randomness that we have already gathered. With that, let us try to again have a look at this, what is one-time pad. Okay, so that is the idea of uniform distributed and independent of plain text. So that means the probability of guessing or the probability of getting head and tail, or maybe whatever may be the probability of for each and every element in that space should be the same. If it has n elements, then the probability of occurring some of this element will be exactly 1 by n, and that should be independent of the plain text. That means plain text might have some probability distribution, but the distribution of the plain text as well as the distribution of the key space should be independent. Okay. The second point is the key must be at least as long as the plain text, because you can understand that in case of our symmetric key, for each plain text I require a ciphertext. That means since it was a 10-bit long or 8-bit long my plain text, my ciphertext is also, my key space or the key is also same length. So both of them are 8-bit long. Okay. Third is the key must never be reused in whole or in part. That means for this message, if you are going to use this key, then this key can never be used for any future message. For example, this is my M. Suppose in my next type, I am going to use say M1, which is different from this message. Okay, what it says that you can never use the same key for any future encryption. Okay, so that is what it says, that the key must never be reused in whole or in part. That means suppose you have used maybe the 50% of the key. For example, this is your key stream, and for say this is your say K9 is also there, and for M1 you just use a shift of this. For M you have used K1 to K9 8. For M1, suppose you are going to use K2 to K9. That means from K2 to K8 you are using the same part of the key with a different message. What it says, you should not use a part or use the whole or in part. Okay, again it says the key must be kept completely secret by the communicating parties. That means both the sender as well as the receiver, they must keep the keys secret. Okay, they should not give any clue about the, I mean any clue means it is, suppose it is in binary, the length of the key is 8, that could be made public, but what is the key values, that information must be kept secret. And if that may be the case, then it can be shown that the one-time password or one-time pad, not password, one-time pad is perfectly secret. So what do you mean by perfectly secret? Okay, let's have a look at this idea. So now for this part, I'm going to use this Jonathan Karj and Lindel's book. Okay, so please have a look at chapter 2 of that book, and this part is taken from their book. Okay, okay. So for that, first let us have a look at what is the definition of perfectly secret. Okay, so suppose this is my encryption scheme. So this is my generation, key generation, encryption and decryption. So you can understand that it has the key part, it has the plain text part, it has the encryption part, it has the decryption part. Okay, so basically it has three parts. Key generation, we call it gen. So key generation, we call it gen, then encryption and then decryption. Okay, so altogether gen, then encryption, ENC and decryption is together, altogether it forms a scheme. So encryption and decryption altogether it forms a cryptographic scheme. Crypto scheme. Okay. Okay. So what it says, an encryption scheme this over a message space M is perfectly secret if for every probability distribution of M, every message small m belongs to M and every ciphertext C belongs to C, for which probability of C is greater than 0, this condition happens. Now you all know what do you mean by this. This is the conditional probability. So I think you all know that what is the probability of M to be equal to small m given that the ciphertext C is chosen as small c. It says that this, even if you have the condition, then also the probability of both are the same. Okay, let us have a look at this. So for the time being, just forget about for all probability distribution M and for every ciphertext C. With this, what is, first let us try to understand what is the meaning of this statement. Probability M to be small m given that capital C to be small c equal to same as probability M to be small m. Okay. Now let us consider, think about a situation. Okay. So this is my M and this is my C and this is my key. Okay. And this C is gone through some insecure channel, and then so this is my encryption and this is my decryption. Okay, so this C is very much known to the adversary. The adversary knows this C. What it says that suppose you have some ciphertext C, then what is the probability that the message was M? That means you are given that you know the ciphertext, C, then what is the probability that the message was capital M? That means in my previous example here, suppose you know this, then you are asking the question, I know this, then what is the probability that the original message was this? Okay, it says that this should be same as even if you do not have any idea about the ciphertext. That means with this ciphertext at your hand, you have no extra information. Okay, so that is the basic idea of the scheme or of the definition. What it says that the probability or the information that you have on the message M is same as the information that you have on the message even if you have the concept of the ciphertext. That means even if you have the ciphertext at your hand, you will not get any extra information about the message. Whatever message, whatever information that you had about the message previously, even if you do not have the ciphertext, is same as the information about the message when you have a ciphertext at your hand. So if this is the case, then we call this as a perfectly secure scheme. So that is known as perfectly secure scheme. Now, what do you mean by the probability for every probability distribution over M? For example, when I talked about frequency analysis, there I have already shown you that in English alphabet, not every alphabets are equally likely. For example, E is the most used alphabets, whereas say Z or W, they are not W, for Z, they are quite less used in English alphabet. Okay, so the probability of occurring E is more than that of occurring Z or W. Okay, so that's very important. That is what some probability distribution is over the message space M. And note that it says that an encryption scheme over a message space M is perfectly secret if for every probability distribution capital over M, every message M and every ciphertext C for which ciphertext C is greater than 0, then the probability of this is this. Now the question is, what we have taken the probability of C, capital C equal to C, to be greater than 0. The reason behind is that what is the conditional? Can anybody tell me what is, say, how can I write it like this? M equal to this given C equal to C. How can I write it? Anybody? Probability, in terms of probability, joint distribution, something. So this is conditional. How can I write it? Anybody?
Probability of M is equal to M.
Yes.
And C is equal to C.
And
C is equal to C.
C equal to C.
And then by probability of C is equal to C.
Very good. Now you can understand that unless this is non-zero, you cannot have division here. Moreover, if what is the meaning of probability of C to be 0? That means the ciphertext, that particular ciphertext is not used anytime. That means you have not used this. There is no chance of using this. So we are not considering that kind of ciphertext. We are considering the ciphertext which have some probability of using. Okay, probability of probability C to be C equal to 0, capital C, this to be 0 means what? This C is never used. That's why this probability is 0. And if something probability of say C equal to 1, what does it mean? That always this character or this ciphertext is always used. Okay, so since we are making it a division with probability of C equal to C, that's why we have taken C to be non-zero. Is the definition clear? Okay.
Yes, sir.
Okay. So there is an equivalent definition of the same thing, and it says that an encryption scheme this over a message space M is perfectly secure if and only if for every probability distribution over M, every message M, and every ciphertext C. Just have a look at, you can use Bayes theorem to convert it. What it says, if you have message this, then what is the probability that C to be C is same as the probability C to be C. So this is condition is given over M equal to M. That means you are given the message and you want to guess what would be the probability of this C. Okay, is same as, even if you do not have the message, the same information. From here to here, it's very easy. You can use the Bayes theorem. Those who have forgot the Bayes theorem are requested to please have a look at the Bayes theorem once again. Then it's not very difficult to convert from here to there. Okay, so that's very important. Okay, the last one is, again, it's a given you a kind of equivalent condition through which you can check whether the scheme is perfectly secret, perfect secrecy is maintained or not. That is known as perfect indistinguishability. Okay, so what is the meaning of this perfect indistinguishability? So everything that what I am explaining here are given in detail in the book by Lindell and Karch by chapter 2. So all of you are requested to have a look at that book to read it in details. Okay, I'm just giving you the basic idea so that it would be easy for you to understand. It says that an encryption scheme this over a message space M is perfectly secret if and only for every probability distribution over M, and mind that initially we have taken only one message. Now you take two messages, this and every C, the probability, if you are given two messages M0 and M1, and I ask you the question, what is the information that you have about C equal to C, is same as this. Note that here for every pair of these messages, M0 and M1, M0 and M1, the property is satisfied. That means you cannot distinguish between M0 and M1. So if you are given M equal to M0, and if I ask you the question, what is the probability of a particular ciphertext? The information that you have must be same as if I change the M0 to M1 and ask you the same question. The same information that you will carry. No extra information. That means if you switch from M0 to M1, you will not get any extra information. And that are very important from adversarial viewpoint. So when you are going to attack some scheme, it might happen that for some message you have some extra information over others. Then it may happen that you may incorporate, or you can use, or you can exploit that fact that suppose M0 will give you more information about the ciphertext than M1, then it may be easy for you to give a kind of counter attack on it. But it says that if your scheme is perfectly secret, then you will not get any extra information if you change M0 or M1. That is why this is for every M0 and M1. Okay. So based on all these properties, it can be proved very easily that what do you mean by the adversarial indistinguishability, and based on that, it can be proved very easily that this one-time pad is perfectly secret. Okay. So what is one-time pad? It's very easy. Just what I explained to you is exactly the same. What is that? First, one-time pad means it's basically doing in binary. So you start with exactly the same proforma that we have already used. So this is your encryption. So here, suppose it's a L bit binary string, say M0, M1, ML, sorry, L minus 1. That's why it's L. Similarly, you must have some keys, that is K0, K1 up to KL minus 1. And you just do the bitwise XOR. That means M0 XOR K0, M1 XOR K1, and so on. Sorry, M L minus 1 XOR K L minus 1. So this is your ciphertext. So it will go through some insecure channel as ciphertext C, and it will reach to your destination as this ciphertext. So ciphertext is C0 to CL, and again you need to put the same key. Note that the same key in a synchronous manner, K0, K1, KL minus 1, and then when you are going to do C0 XOR K0 and CL minus 1 XOR KL minus 1, you will suddenly get back the plain text, and that should be equal to your M0, M1 and ML minus 1. Okay. So that's exactly one-time pad. OTP, not one-time password. Okay, let's have a look at formally. So it says that fix an integer L greater than 0, then the message space M, the key space K, and the ciphertext space C are all equal to 0, 1 to the power L. Why? Because this is an element of what? 0, 1 to the power L. One element is this. Key space is also an element of 0, 1 to the power L. Why this is 0, 1 to the power L? I hope that you all understand what do you mean by 0, 1, say Q. How many elements are there here? Anybody? Can anybody tell me how many elements are there?
Sir, 8.
8 elements. So it should look like 0, 1 cross 0, 1 cross 0, 1, right? So how many elements are there? 2. So how many elements that, for example, say 0, 0, 0 is an element of, you take 0 from here, 0 from here, 0 from here. Similarly, 0, 1, 0. You take 0 from here, 1 from here, 2 from here. So at this position, you have 2 options. At this position, you have 2 options. At this position, you have 2 options. So for each of them, you have basically 4 options for other 2 options. Okay. So altogether, there will be 2 into 2 into 2 elements. So 8. So how many elements are there? So here 0, 1 to the power L, the cardinality will be exactly 2 to the power L. Similarly, it is also cardinality 2 to the power L, and ciphertext space is also 2 to the power L. So that's why. So the key space, the ciphertext space, and the message space, all of them are of equal size, having 2 to the power L many elements. Okay. The key generation algorithm gen works by choosing a string from K according to the uniform distribution. That is, each of 2 to the power L strings in the space is chosen as the key with probability exactly 1 by 2 to the power L. For example, suppose you have, say, L equal to 2. That means in your 0, 1, 2 to the power L equal to 2, how many elements are there? 4 elements are there. Who are they? The elements are like 0, 0, 0, 1, 1, 0, and 1, 1. So they are the 4 elements. Now, uniform distribution means probability of occurring any of them is how much? Suppose, what is the probability of occurring this? Anybody? What is the probability of occurring this? Is
So
what
1
should be?
by 4.
Yes, 1 by 2 square. That means 4. Here also, so you have how many elements? 2 to the power L many elements in K, and the probability of occurring each of this element will be 1 by 2 to the power L. Okay. Encryption. The encryption works as follows. Given a key belongs to this, that means this is a basically K L component binary string. You can understand this is 0, 1, 0, 1 up to this L bit long. And the message M, this is also 8 bit long. Output will be C equal to K Xor M. That means each, it will be done bitwise. So K is nothing but, say, K0, K1, KL minus 1, and M is basically M0, M1, ML minus 1, and do the component wise bitwise XOR. Whatever be the output will be an L bit long ciphertext. So the decryption will follow like this for the same key. Note that for the same key, the ciphertext will be M ciphertext XORed with the key that will give me back the M. So that's the basic idea till now what I have just explained to all of you. Is it clear? Is it clear?
Yes, sir.
Okay.
Yes, sir.
Now, it can be shown that by the lemmas that just now I have explained to all of you, this lemma and this lemma, it can be proved that this one-time pad is a perfectly secure, it's perfectly secret. I'm just giving you just the basic idea. So everything is taken from Lindelkirch's book. So there, everything is given in details. What it says, fix some distribution over M, because you don't have any control over the message space. You have only control over the key space, because the key will be uniformly distributed, but you can never have a control over message space. Suppose in English language, you know that E is the mostly occurred alphabet. And fix an arbitrary M. Choose any arbitrary M and C from C. The key observation is that for one-time pad, what is this? You have given M equal to M. What is the information that you are getting about C? Now, how the C is obtained? C is obtained how this M plus K equal to C. So they are random variables. Mind that. How you get C? C is nothing but message Xor K, and that is C. And you are given M equal to, your M is fixed, right? So that is same as the probability you just put in place of M, because this random variable is given the value, taken this value M. So you can put M. Note that this conditional mark is now gone. So you are using the fact that M is small m. So you are putting M is small m plus this equal to C. Now this is a random variable, so you can check because both side, if you take Xor of M, so here this Xor will vanish, because M Xor M plus K, M Xor M will, because if both of them are of the same bit, then that becomes 0. So that becomes K equal to M plus C. Okay, so that is K equal to M plus C. Now you know that the K, what is the distribution of K? In case of one-time pad, the take whatever may be the K, the distribution will be 1 by 2 to the power L. Okay, since this holds for all distribution and all M, we have that for every probability distribution over M, for every M0 and M1, and for every C, the probability of, so this is same as 1 by 2 to the power L. So this will be same for any M0, whatever may be, M0 or M1, it doesn't matter, is same as this. So from the distinguishability lemma, just now we have shown that perfect indistinguishability lemma. So this is perfect secure if and only if this will satisfy. Okay, so from this lemma, you can prove that one-time pad is perfectly secret. Okay, so is it clear to all of you?
Sir, I have a question that for second line, probability of
This one.
M. Yes.
Yeah. So you are using the fact that what is this conditional probability? What is the meaning of a conditional probability? So probability, say x equal to a given say y equal to b. What does it mean? Y equal to b is given. That means you are already having some information at your hand. Based on that information, you are trying to find some information about x equal to a. So that is the meaning of conditional probability. So this information is already at your hand, right? Now,
Yes,
when you are doing so, so here M equal to capital M equal to small m. So that information is already at your hand. Now you are using that information here. So when you are going to use, so you know that capital M value is always small m. So you are now using this fact here. So you do not need to use any conditional, because this condition is already used here by changing capital M to small m, and that becomes equal to C. Now you do not have to use any condition values. Okay, and then you just switch from here, this side to this side, you can take it out, and that
sir,
becomes.
is there any other M which is Xor with the other key and to get same ciphertext C?
Okay, so what will happen then? Let's see what you're trying to say. Suppose what is your fixed? M is fixed, right? What your question? Could you please repeat? Yes. So your aim is fixed and you put some say K1 and you say that the same ciphertext will generate, right? For the same aim K2. That is your question? If that is the case, then what will happen?
No, sir. If
Yeah. What is your question? Can you
sir,
please
if
repeat?
aim is also changed, if we change the sir K fixed, and if
Yes.
aim changed,
Yes.
so we can get the same C.
That means like this, aim M1 K1. Yes, that may happen. That will certainly happen. Because all this C1 and C2, these values is either 0 or 1, right? Suppose this value is 1. So this value, sometimes it has to be also 1. Then in that case, both of them will be same. But here, you are making it as a fixed. So here you are making aim as fixed. This information you are using. That's why you are putting this value m, because you are using the fact that m has been chosen as small m. So this here the message is fixed. Once you are starting with an arbitrary message, then you do it for the same message. You are working with the same message. And that is the probability. See, m plus c, what is the value of this k then? The probability of choosing this m plus c is exactly the 1 by 2 to the power L, because that is the key distribution. Whatever the value of k, whatever be chosen, so this is chosen as your key. How the keys are generated? So keys are basically, so m plus c equal to your k. So k, sorry, not m plus k equal to your c. So if you add both side m, then m plus k will give you m plus c. That means this value will become 0. M plus m is 0. 0 plus k is k. So k equal to m plus c. And since this k are distributed uniformly, the probability of k, whatever may be the value, this is always 1 by 2 to the power L. So from whatever be the values of m, you will always get this value as 1 by 2 to the power L. Now is it clear?
Yes, sir.
Good. Okay. So now can anybody be able to tell me, it is perfectly secret scheme, encryption scheme, then why don't we use the one-time pad? Any idea why we don't use one-time pad for practical purposes?
So there is a two big problem. So one
Okay.
is if length is short, then the key space is very short, 2 to the power L. Then we
Okay.
can execute exhaustive search and we can find out the key. And the
Okay.
other is if the length of the message is very high, then there is a problem to sending key to sender and receiver.
Okay. Yes, very good point that you have raised. But formally, let us try to have a look. See, the first point that you raised is basically the key length size, right? And the key length size could be at your hand. So if you think that say 2 or 3, maybe 10 or maybe 20 length key is short enough, then you can certainly increase the 20 length key. It may be 140 length or maybe 200 or 2000 bit long key that you can use at the same time. Okay, so the point is this, from here it will be clear. It says that for any scheme, encryption scheme, chain encryption and decryption is perfectly secret encryption scheme over a message space M. Let K be the key space as determined by gen, then the size of key space must be greater than equal to size of the message space. So in case of Varman or one-time pad, the size of key space and the size of message space were all all 2 to the power L. So if the message space size is 2 to the power L, the key space size is also be 2 to the power L. The ciphertext space size is also 2 to the power L. So this property is satisfied. But it says that if the scheme has to be a perfectly secret encryption scheme, then the key space must be at least the size of the message space. As a result, when you are going to encrypt some message, for example, suppose you want to encrypt a message, just now what my dear students who has just now explained, suppose you are going to encrypt say 1,000 or 10,000 bit long message, then to encrypt this, you have to use a key which is also 10,000 bit long. So this should be the key, must be this. Otherwise, if you make a less, say if you use say 200, or even if you use like 9099 length, then also it can be shown that if you are going to use, then one bit you need to reuse, a part of it you need to reuse of it. If you are going to do so, then also the scheme cannot be a perfectly secret scheme. So to achieve the perfect secrecy, you need to have the key space size should be at least the message space size. As a result, if you are going to encrypt a long message, you must also need to encrypt or to have a key of size at least that size. That means 10,000 bit long. So you can understand that suppose A wants to communicate with B with say 100 MB data. Now you can understand that how much big. So the key size will be at least 100 MB. At least 100 MB. So before doing any kind of conversation, this key, both the A and B must share. So if the size of the key space is such a big one, then how to share them efficiently? So that's a very big question. So it's really difficult to then communicate with each other securely. But if that can be done, and if that kind of keys are being used only once for every encryption, then that can achieve a perfectly secret secrecy. And for military purpose or for sometimes very very important hot talk, these hot lines are done implemented through this kind of schemes, one-time pad. So in one video, I'm not sure about it, but in one video I also heard that the US and the Russia, when they talk with themselves, then they use this kind of one-time pad secure channels are being used for that. That means in both sides, they for only one time use, they communicate with each other very securely, maybe physically. They cannot send this information. They physically they transfer this key to the other part, and when they have the key, then only they send the encrypted message by using this. So it's very costly and it's very difficult to achieve, because it's very, in that case it would be not very convenient to have, if you have some means to communicate with say that big key with each other, then why not you communicate with this message directly. So that was one of the big drawbacks that one of the students has already mentioned. That's why one-time pad is not very frequently used for practical purposes. In Lindelkaj book, they have given a kind of small note. They say that the above theorem shows an inherent limitation of schemes that achieves perfect secrecy. Even so, it is often claimed by individuals and or companies that they have developed a radically new encryption scheme that is unbreakable and achieves the security level of the one-time pad without using long key. The above proof demonstrates that such claims cannot be true. The person claiming them either knows very little about cryptography or lying. I'm not using this word, or lying. Okay, so that's a quite interesting remark that is given by Lindell Kaj in his book. In second chapter, you can find this. Okay, so the question is, if not, then how to communicate with each other very securely? So that's now the next question will certainly be raised. Then how to communicate with each other securely using the symmetric key? Because the symmetric key, just now when I started my lecture, I have already shown you the kind of scheme, and that looks exactly the same as one-time pad. So this is my encryption and this is my decryption, and the most important part is the key, and in both cases the keys must be the same. So the question is how to communicate or how to send the key. Will that be always same as the length of the message and same as the length of the key, or will there be any part of it, for example a small k, maybe k bar, could generate the key string? And if you communicate this small k bar in both sides, then it may be sufficient to generate the same key. That means that the key generation algorithm gen, if it takes a small k bar which is capable of generating the capital K or the key, then it may be sufficient for both the parties to exchange only that small k bar securely. And suppose this Jane algorithm is known to all, that means for sender and the receiver, both of them, also the adversary, they also know the Jane algorithm. But if some password or the small portion of the thing is generated suitably, and if that is very easy to communicate, then it may be the case that with that Jane algorithm, which is known to sender, receiver, as well as the adversary, but the adversary has no clue about the K bar, only the sender and the receiver, they know K bar, then from there, there might be a chance of getting some long key stream. So now I'm going to explain you how that can be achieved. Okay. Okay. So let's again have a look at this. So what is important here is that some random looking K must be there. Just now we have seen that in case of perfectly secrecy, it should be uniformly distributed. But one of the ways to generate that uniformly distributed thing is that you can make a coin toss. For example, if you want, say, 10,000 times, you can use 10,000 times coin toss by some unbiased coin. But the problem would be if you generate this 10,000 bit long keys, then if you by some means, if you transfer the same coin to this guy, and if he starts doing 10,000 times coin tossing, then I am sure that it is almost zero probability that he will get the same key here with the same coin tossing, even with the same person who tosses the coin here. Okay, that means if I use the coin tossing mechanism for both, we know that the coin tossing mechanism, if you start with some unbiased coin, then you will certainly get an then certainly you will get a random sequence of zeros and ones. But the problem is, if you have the same coin and maybe the person who make a coin toss, if you send him personally to the receiver, and at receiver ends, if he again continues 10,000 times the coin tossing, I'm sure with with almost zero probability, he will again get the same key what he really obtained at sender end. Okay, so that coin tossing business is not suitable. But we need something which will really generate some random looking strings. Okay, so in cryptography, that's why few things are important. So the first one is random number generator, random number generator. Second one is that pseudo random number generator, pseudo random number generator. That means pseudo means it's not exactly the original one, but almost. And third one is cryptographically secure, cryptographically secure pseudo random number generator. So RNG is very well known in crypto community, PRNG. So this is known as PRNG, pseudo random number generator, and this is PNG. Sorry, RNG, random number generator. So random number generator, pseudo random number generator, and then cryptographically secure pseudo random number generator. Okay. So what is the example of a random number generator? For example, if you make a coin toss, you will get a sequence of zeros and ones, and that would be a random event, and that you can associate with this pseudo random number, random number, truly random number generator. So you can put it like truly, like compared to this, you can put it truly random number generator. So sometimes it's written also TRNG, truly random number generator. For example, the random number, so there may be many events. For example, sometimes on the screen, so the positions where, say, I put my mouse, the locations, based on that location some random number may be generated. Or suppose I have some type speed on my machine, I use some kind, for example, A, B, C, D, etc. So if I press some key and the time that it takes to, how much time that I press that A, it vary. For example, suppose I press A for maybe 0.0001 second, and maybe say B, when I typed it, I pressed it maybe for like this. Or even if you can make it more maybe like this, more appropriate, or like this. So from there also some random number generators could be generated. So they are truly random, but the problem is, if you have some random numbers, from there you have some kind of distribution, and if you associate with your key space, then the problem is, how will you generate the same thing on the receiver end? Just like coin tossing, as I mentioned, you cannot generate the same sequence of zeros and ones on the receiver end. Maybe you can generate, but with a very less probability. Maybe this with the same coin and the person who coined the who tossed the coin, maybe for him or her it's really not almost possible to generate the same thing at the receiver end. So this cannot be used for practical purposes. Okay. So now the question is pseudo random number generators. Pseudo means it's really not that random, but it almost looks like a random thing, and that can be also generated. That means your machine, some algorithm can generate this. You can understand that if some algorithm generates some number, then it can never be a random number, because if it's some algorithm generates, that means it has some property, and it has some, it's actually following some rules. If it follows some rule, how can it be random? But for pseudo random, it's following some rule, but somehow it has some similarity with pseudo randomness. Okay. Sometimes in C programming, very often we use for random number like rand function. I think you all must have used the rand function in C programming, in ANSI C maybe, ANSI C. Okay. So if you look at how this rand functions is generated, so I'm giving you, this is as an homework. You may not directly get, you need to do a little bit of data mining in Google, how exactly this rand function works in ANSI C. Maybe in Windows or Linux, it may be different for both of them, but how it works, or how the srand function works. So in my next class, I will ask you this question, how they work, but they must have some kind of property. What is that property? Let us have a look. So this is S0, and this is, so S0 is 1, 2, 3, 4, 5. S0 is 1, 2, 3, 4, 5, and Sj, say AS J I plus 1 maybe, so J plus 1 equal to 1, 1, 0, 1, 1, 0, 3, 5, 1, 3, 5, 1, 5, 2, 4, 5, 5, 2, 4, 5, S J plus 1, 2, 3, 4, 1, 2, 3, 4, 5 modulo 2 to the power 31. Okay, what does it mean and how it works? So it looks like, so start with S0, then what is your S1? S1 equal to 1, 1, 1, 3, 5, 1, 5, 2, 4, 5 S0 plus 1, 2, 3, 4, 5 whole modulo 2 to the power 31. So you have now S1. What is S2? S2 is whatever may be the value. S2 is this value. So 1, 1, 0, 3, 5, 5, 2, 4, 5. Then S1 plus 1, 2, 3, 4, 5 modulo 2 to the power 31. So you can
One is
understand.
missing.
Anyway, whatever maybe. So anyway, you will finally start with S0, S1, S2, and so on. Okay. So that means this rand function has a close connection with this polynomial. And this is a way how this rand function is generated in ANSI C. So not all the bits are used, some bits are used. So that is your homework, how it actually works. Okay. So here you can see that the first term is this, second term is the, third term is this, and so on. But if you look at it mathematically, how it looks like a polynomial like this, y equal to ax plus b. Okay. So where if you know this value, then you can calculate this value, where a and k or a and b are fixed. You can see that this is your a and this is your b. So a and b are fixed. Okay. So if you do it in cryptography for doing the randomness, then there will be a problem. Can anybody be able to tell me what could be the problem? I'm giving you a kind of attack model. Okay. So suppose so that means if you know, so this is a 1-degree polynomial, right, with 2 variables. Suppose you know 2 consecutive values, say S1 and S2. Suppose you know. Will you be able to find? Will you be able to find what? A and B? So suppose you know few fixed values. So A and B are fixed, right? And if you know 2 consecutive values, then what will know? So you know 2 consecutive values means you know first this one and then second this one. Then from these 2 equations, you will able to find the value of, because consecutive is required because you know then x value as well. Then from there, you can very well calculate the value of A and B. what I want to say is that this rand function is not cryptographically secure because it's just a linear function. It's a two variable function, and by putting it proper values, that means if you by some means if you know two consecutive values, then you will able to find the values of A and B. So it may be here it is using this, you may use some other values here to get your own random values, random functions. But wherever you are doing this, if you know two consecutive values, then you can break this. That's why this scheme is not cryptographically, this rand function is not cryptographically secure. Okay, so we require some cryptographically secure pseudo random number generator. Okay, let us have a look at something which is also of course not very secure, but that is very important. So what is our main idea? Main idea is to generate a key stream. So suppose I want to generate a 15-bit key stream, but as an input I give some 4-bit of input. Say I give say 1100 as input in both sides, and that input will be sent through a algorithm keygen, and that will give me a 15-bit long key stream, which is almost like a random, not a complete random but a pseudo random, say 15-bit. So similarly, if you put it here, the key stream keygen, gen, and that will give you a 15-bit key. Now you can use it in here in decryption, and here you can use it in encryption. Okay, so what is important here? You can use 4-bit to get 15-bit output. So in case of one-time pad, you have to put this 15-bit, but now instead of 15-bit you are getting just a 4-bit. So in general, if it could be a case that if you put L-bit, you will get a 2 to the power L minus 1 bit long key stream. Then it would be nice for you because you are sending only this L bit that is capable of generating almost random looking things, which is of length 2 to the power L bit, 2 to the power L minus 1. So you now can encrypt a 2 to the power L minus 1 bit long plain text message. So that will be nice for us if we can, by some means, if we can do that. And that can be done by using a very important concept in crypto, especially in symmetric key, that is known as LFSR. LFSR. That full form is linear feedback shift register. Okay, so what does it mean? The basic idea is, suppose I have a kind of register, say I have say 5 register or 5 boxes. You can think of 5 boxes. Okay, the idea is this: they are connected with each other. At each round, the data, whatever is there, so each of the boxes is capable of storing either 0 or 1. It can store either 0 or 1. Okay, so at each round, each of the value what is stored here is shifted from right to left. That means suppose you have say 1 1 1 1 0 present here. I'll put it 1 1 1 1 0 present say at round 0. So what did happen? it will shift in the round 1, it will shift each of them to the left, and whatever was there at the first box, it will come as an output. So 1 will come out as an output. So this is my output. So this should not be in round 1. So this should not be in round 0. It should come out in round 1, because everything will be shifted towards this side. So this will be shifted out. As a result, this will come as an output. Okay. So what will be there in the box? Let's see. Okay. So it is not only shift, then it should be only shift register, but it says that it should be feedback also. So some feedback will also be there. So let us have a look at what does it mean. Feedback means what? So suppose I write it like C0, C1. So this is my C0 in terms of matrix. The box is basically the first index is C0. I write it C0, C1, C2, C3, C4. Okay. So this is if I call the matrix C, then C0 is basically this box. C1 is this box. What I'm going to do is that I have some feedback connection like this. Like this. What I'm going to do, in the next round, it will be shifted. This value will be shifted from here to here. No problem. That is fine. That means in the next round, it will be shifted 1. Everything will be shifted 1. So that means it will come, it will go out. So it will come here, that is 1. It will come here, that is 1. It will come here, that is 1. It will come here, that is 0. Now the question is, what will be given to the last box? And that is why it is feedback. The last box will be like this. So it will be the XOR operation of the first box, this box, third box, and the fifth box. That means it will like, so 1 plus, it is the third box, 1 plus, it was my last box, 0. So that means 0. Okay. So this is round 1. So what will be there in the round 2? Can anybody tell me what would be there in the round 2? So it will be shifted here. So as an output, I will get 1 here. So it will come here 1, 1, 0, 0. Now this box is empty. So what should I write it there? The box of this one connected with this one, connected with this one. So this, and this. What should I write? It should be 0.
0.
Yes. So can you please calculate quickly what should be the rounds and when the same thing will occur? 1, 1, 1, 1, 0. The same. If the box will again contain the same thing, then it will again generate the same output. So they are my keystream bits. Okay. So they are my keystream bits. So quickly, can anybody generate? Okay, let me put it there. It would be easier then. Yeah. So what would be in round 3?
1 0 0 0 0.
Okay, 1 0 0 0, and then it will this box, and this box, and this is 0. Check, this is not same as this, right? Okay, in round 4, so here the output will be 1. Quickly.
0 0 0 0 1.
0 1. So this is 4. Then 0 0 0 1, and then this box, and this box. What will be the case here? It should be
1.
1. So this is 5. So here I had 1, here I had 0.
Sir,
Sir, in round
after
3,
round 2,
Yeah,
so round 3, yes, sir, feedback
round 3.
is 1.
This,
Yes,
and
sir.
yeah, it should be 1. Right. It should be 1. You're right, because this one, and this one. So this, and this, it should be 1. You're right. So I need to put it this. So it should be 0, 0. It should be 1 here. Now you just please modify it accordingly. Okay. So just have a look at the code here. I have a code here which will help you in giving the answer. Maybe, yeah, LFSR. So this is my LFSR. Here it's 0, 2, and 4. So you can see here my 0, 2, and 4. So this is my 0th box. This is my 2nd box. And this is my 4th box. I mean 5th box actually, 0, 2, and 4. Index wise, 0th index, 2nd index, and the 4th index. So I have made a programming of that. I started with the input 11110. So this is my 11110. And if you run this, you'll get the output. So this is my box. So this is my round 1. It gives me output 1, 1, 1, 1, 1. First, look at the outputs. So if you look at the first 5 rounds, so I started with 5 states. So they are called states, initial states. So whatever they are in the register, so each box is known as registers. Okay. So in the starting box, I started with 1, 1, 1, 1, 0, just 5-bit. Okay. If you look at the outputs here, 1, 1, 1, 1, 0, that means whatever was there at my initial state of the registers, it will give me all the things as an output. So I started with 1, 1, 1, 1, 0, it gave me 1, 1, 1, 1, 0 as an output, and then something else. Okay. And what I did if it starts with the same initial state at round 15, if you look at this, at round 15, it is again the same state. And if it comes to the same state, then it will again repeat the same pattern. It will again repeat the same pattern. So 1, 1, 1, I just did it for 20. If I make it for 30, then you will be able to see that it will again generate the same pattern, because the initial state is same. So it's again a repetition. You can see that again at 30th step, it's again a repetition. So maybe if I make it, reduce it a bit, okay. You can see that it starts with 1, 1, 1, 1, 0, 0, 0. It will also have the same pattern, 1, 1, 1, 1, 0, 0, 0, the same pattern, because this state and this state is the same. So if it starts with the same state, then it will also give you the same output. Okay. But note that for 5, so how much it was? 1, 2, 3, 4, 5. It gave us the 15 distinct, this period is 15. Again, it's repeating. So we call it 15, this period. So the period of this LFSR is basically 15. We started with 5. Note that for LFSR with L states, so here we had 5 states, it should be at most L to the power L minus 1. Okay. So for L equal to 5, so it should be 31, but still it's giving me 15. After 15 steps, it's again repeating. But note that for 5, I started with this 5 state. If I send this small key to the other guy, then he also able to generate the same key stream like me. This same key stream like me, but he will get a bigger key stream like 15. And mathematically, it can be proved that for L initial state, you can generate a key stream of at most 2 to the power L minus 1 bit long key stream. That means it will be your initial state that will be able to generate at most. So here it could be 31, but you see that after 15 it's again repeating. But if you choose carefully, then it will be able to give you a period of length 2 to the power L minus 1. That means 31. So I'm not going to, so finite fields are used here. So Galois fields constructions are used here to show that 2 to the power L minus 1 could be the period, but I'm not going to details of it. But if somebody is interested, he or she may have a look at this. But the idea here is that this is basically a kind of linear feedback shift registers, because this is very fast in hardware. In hardware, you can implement this. It's only a shift and few tabs are there. So in hardware, this could be very fast. Now, this tab could be anything else, somewhere maybe here, somewhere maybe here. Depending on that, your connection will be different, and depending on that, your output will be different, even if with the same initial state. So here, this LFSR will be public, but this initial state, that means the key embedded in it, will not be public. That will be transferred securely, and that is capable of generating a maximum period of 2 to the power L minus 1. Okay. So for stream cipher, this LFSR was highly used because it was very easy to generate and it's very efficient. But again, it will also have a similar. So this is a linear feedback shift register. That means the recurrence relation, if you look at that, that is a linear function. And if it is a linear function, say of say L bits of initial states, then it might happen if you have L plus 1 many consecutive bits of the key stream, then you are in a position to get the whole key stream. Okay, that means if you by any means, if you come to know only the L plus 1 bits of it, L plus 1 bits of key stream, and that too consecutive, then you will able to guess the maximum length of 2 to the power L minus 1. Then you are basically done. That's why there are plenty of such attacks which are already mounted on linear feedback shift register. That's why you cannot directly use as a key stream generator for a system, because you might have some idea about L plus 1 consecutive bits, then the scheme is completely broken. Okay, so that cannot be considered to be a nice scheme. Okay, then the question is what? And many people tried to do many things, and research continued for a long, and then a scheme which is quite popular came into picture, and that is known as RC4. Okay, so let's have a look at directly maybe from the Wikipedia. So it's RC4. It's one of the most popular stream ciphers that were used. Currently, it is not actually used anymore for any practical purposes, but this RC4 was one of the most favorite stream ciphers of all the time, because it's very simple to implement for both software as well as hardware viewpoint. It's very fast and it was quite secure, but few interesting attacks has been mounted on it. As a result, it was collapsed, and nowadays it is no more. But you'll be surprised to know that it was one of the popularly used ciphers, even used in TLS, the protocols. Those who are aware of these protocols, TLS protocols, they may find that it was quite interesting, and it was also used. So historically, it's quite famous or popular. So it came into picture in around, just have a look at this, the historical development of it. It came into picture by Ron Rivest of RSA Security in 1987. So it came into picture in 1987, and it was officially termed as Rivest Cipher 4. The RC So you remember the RSA crypto system, the reverse Shamir and Edelman, the same guy reversed. So this was termed as reversed cipher 4. That's why RC4, the RC acronym is alternatively understood stands for Ron's code. So Ron reversed, that's why Ron's code. Okay. RC4 was initially a trade secret. That means though it came in 1987, it was a trade secret. That means nobody knew about what was the cipher. Everybody could find it in embedded in some software or embedded in some hardware or something, and everybody could see that it works very fast. So it was code secret. As a result, very few people who are related to that company, only them, they know the what is the exact code of RC4. Okay, but it was a nice just a minute. It was a kind of nice idea that suddenly it came out of the I mean, it became public, and somebody made it public, the code, and then many guys, they tried to judge whether that is a real RC4 or not, and suddenly they came to know that whatever code was leaked is basically the RC4 code. As a result, the code of RC4 was no more secret, so everybody could find it. And suddenly, in around maybe you can see that RC4 became a part of some commonly used encryption protocols and standards such as WEP in 1997, WPA in 2003-4 for wireless cards, and SSL in 1995, and successor to TLS in 1999. So in 1999, it became in every wireless, even for protocols, even it becomes one of the integral parts. Okay, until it was published for the version of TLS by RFC something in 2015. So up to 2015, it was considered to be one of the most popular ciphers used in for cryptographic purposes due to the RC4 attacks weakening and breaking RC4 used in SSL or TLS. The main factors in RC4 success over such a wide range of application have been its speed and simplicity. So it was very simple and very easy to implement. I'm just going to give you the description of it in a simple way. So it has basically two parts. So one is key scheduling algorithm, which is known as KSA, and another one is basically the pseudo random generator algorithm, PRGA. Okay, now you can see from here, this is only the part of key scheduling algorithm. It's very easy, very simple. What it is doing? So key scheduling algorithm is used to initialize the permutation in the array S. Key length is defined to be the number of bytes in the key. Okay, suppose okay, let me show you one of the implementation done by me. So it's RC4 encryption. Okay, so so this is the code. Okay, so somebody want to encrypt some message. Anybody tell me some message you want to encrypt? Anybody?
We are learning cryptography.
Okay, we are learning cryptographic. Okay, and say my key is Avishek. So how many alphabets are there? 1, 2, 3, 4, 5, 6, 7, 8. A, V, I, S, H, E, K. Seven alphabets are there in my password. Okay, so that key length is here 7. So this is my key length, and this is the 28 characters are there, including space, in we are learning cryptography. So if you run this program, then you will find that this is my total ciphertext. Okay, this is in binary, so you can make it in hex or whatever. Just keep in mind that I have to remove this dashes when I am going to decrypt it. So 3 dashes will be there. Okay, now I put this thing to the decryption algorithm. Let's see where it's, yeah. So this is my decryption algorithm. So I'll just put it here. Whatever. See, I may put it, copy it once again. I need to remove 3 dashes. So here 1 dash, just double look. So this is another dash. They are basically for new lines. Okay, this is another. And you remember it is a symmetric key. So here I am also using the key Avishek. And if you do so, I'll get we are learning cryptography. Okay. So that's the ciphertext. Now, if you convert the ciphertext into the corresponding characters, you will get back this message. So that's the RC4, and that's very easy to see or easy to understand the code or the pseudo code given by Revest, but it's very difficult to understand why it is working. And unlike LFSR, it has a very long period. I forget, around 2 to the power 32 is the period size. I exactly forget the length of the period, but it's very long. So you can understand just having a password of length 7, or you can consider 7 into 8 bits long. So maybe so 56-bit long password, and it's producing 2 to the power 32-bit long period. So it's a very high, and it's very fast, and it's very easy to understand, and it's very easy to implement. So it's basically, the first part is the key scheduling algorithm. It's very easy. It's basically each of them are bytes. So each boxes are considering one of the bytes, and then it's basically doing some class operation and then swapping operation, nothing else. So it's very easy in hardware as well as in software. And then it's doing the pseudo random generation algorithm, and that's also very easy. So it's basically doing some addition and then finding this value s of s, that's all, and then output k. Now this is only the key generation as well as the pseudo random number generation and the key scheduling algorithm. So for my case, I have also included like taking the input, then converting the input into binaries, then I apply these 2 codes and I get a key stream, and then sequentially I matches with my plain text and the key stream, and whatever I get, I put it as a ciphertext. Now I send the ciphertext to the receiver. In the receiver end, he or she is also going to use the same password as me, like Avishek. And when he or she gets this ciphertext, he or she get back the plain text. That's all. So that's the RC4. So as an homework, I put it on your side to implement this. You can implement in Python. I put it in Sage. In Python, it's the same. It's almost the same code as Python code. So please implement this and show me. So that's all. So any question till now? Anybody?